not good. New methods, they're trying out a new method, and they're taking a sample of 40 soil samples and to see how much lead was released, and they're noticing that, hey, our average is 83 parts per million with a standard deviation of 10 parts per million. Now the question is there significant evidence, and we're going to pick the 5% level here, that the new method releases less lead? Or is this sample of 40 maybe just a fluke, right? I mean, 83, it looks like it releases less lead, but is it a result so far from our original that it causes us to disbelieve this original claim of 86? So that's what we're going to test. We're going to use our 4-step process, and because we haven't been given a population standard deviation, we are going to use a t-test. All right, step 1 is going to be to identify the population, the parameter, the null hypothesis, the alternative hypothesis, and the alpha, the significance level at which we're going to test this claim. That's actually been given to us. We're going to test it at the 5% level, so I'm going to say alpha equals 0.05. My population, I am testing a certain type of soil, so my population is all soil of this type. Right? It only applies to the type of soil that they're working with, right? The parameter here is the true mean, that's mu, lead released. Our null hypothesis is that this new method is no better than the old method. The new method releases the exact same amount. This low number that we're seeing here is simply a result of happening to pick a lot of samples that had low lead maybe originally. And the alternative hypothesis is that, yes, this works, and it is less than 86 parts per million. So our new method is actually releasing less lead, which is a good thing. All right, so with that established, we're going to move on to step 2. Step 2. Step 2 is where we acknowledge and recognize the conditions of this problem. There are 3. 1, that our data set comes from a simple random sample. 2, that it's normally distributed. And 3, that our samples are independent. So, unfortunately, this problem doesn't tell us that we're taking a simple random sample. This might have been 40 samples of dirt in a row, or specifically from the same soil type when they were doing a day's worth of excavation. So we must assume that the sample of 40 applies to a wider range maybe than it actually does. Normality doesn't tell us that we're normally distributed in the problem, but because we have a sample size bigger than 30, n is greater or equal to 30, we have the central limit theorem kick in. So yeah, we've got a normal distribution based on the central limit theorem. And independent mining removes a lot of material from the earth, and so we can say all soil is definitely greater than 10 times the 40 samples that they took. So there's a lot of dirt out there, there's a lot of rocks and whatever. There's a lot of stuff that they can mine, and so independence, a non-issue. So aside from the simple random sample, looks like our conditions are good to go. This might come back to haunt us, we'll see. Step 3, I recommend doing the calculations in your TI calculator. Step 3 looks like this. We are doing a t-test. Now, a t-test is very, very similar to a z-test. It's still going to be the sample mean minus my hypothesized mean divided by, here's the switch, we're looking at a sample standard deviation because we don't know the population standard deviation. This is actually more realistic than a z-test, divided by the square root of the sample size. So, we already have these numbers. Just going to drop them in. 83 minus my null hypothesis of 86 divided by my sample standard deviation of 10 over the square root of my sample size, which is 40. I ran this on my calculator a little bit earlier, and this gave me a t equal to negative 1.89. Now the negative is a good thing because my alternative hypothesis was less than, so this means our standard deviation is below the mean. If I was to draw a picture of this, here's my mean right there in the middle. Negative 1.89 standard deviations brings me like there. And so we're investigating that zone. How big is that shaded area? Well, the p-value, the probability of being less than or equal to negative 1.89 standard deviations is equal to 0.0326. So there's about a 3% chance we're in this shaded zone. Because we're testing at a 5% significance level, well, I'm getting ahead of myself. Let's jump on over to step 4, our conclusions. All right, step 4, conclusions. Now, we need 3 things in our conclusion step. We need evidence, which is going to lead us to making a choice about our null hypothesis, and then we're going to frame that choice in the context of the problem. So evidence, choice, and context is where we want to live. Now, the evidence is that our p-value, the probability of seeing a result like this 83 after a sample of 40, the p-value was equal to 0.03. It's a 3% chance, which is less than our alpha at 5%. So with our p-value less than alpha, the choice is obvious. We are going to reject the null hypothesis. All right, so we're rejecting the null hypothesis. What does that mean in the context of solving this problem about lead in the soil? Well, it seems that the new method releases less lead. Now the practice problem goes on to say, hey, there might be something iffy with this. Is the new method really better? Well, part 2 says, what could we do to make it a better study? Well, that's where that simple random sample comes in. If we truly had a simple random sample, if we tested more than one type of soil type, we could actually say that this method is truly better. However, with no simple random sample, our results are limited to the specific type of soil that we're dealing with. So there you go. There's practice 12.1.1.